Hello, my name is Rafael Henriques. I'm currently doing my postdoc at the Champalimont Center for the Unknown, and I have been an active DIPY contributor since the start of my PhD at the University of Cambridge. Today, I'm going to talk about diffusional kurtosis imaging. Diffusional kurtosis imaging, or DKI for short, is a phenomenological model. This is, DKI tries to represent signals' properties without postulating hiding biological mechanisms. This technique was proposed in 2005 by Jensen and al. How DKI differs from DTI? As Ariel presented in the last talk, DTI quantifies the anisotropy of diffusion from data acquired with different directions for at least one B value. DTI assumes that diffusion is Gaussian, and therefore, its model expects that the log signal decay has a function of the B value varies linearly for each gradient direction. However, in real tissues, one can observe deviations from this linear decay due to non-Gaussian properties of diffusion in tissue. DKI is an expansion of DTI that tries to capture this non-Gaussian behavior using information from multiple B values. This is also known as multi-shell acquisitions. So why diffusion is Gaussian in tissue? While in free water, the displacement of the diffusion molecules is expected to follow a Gaussian distribution, as shown here in the distribution in blue. In tissues, we will see a deviation from this Gaussian distribution, marked by the distribution in black. This is because in tissue, molecules are in constant collisions with tissue boundaries and obstacles. Moreover, even ignoring these collisions, non-Gaussian information is expected to occur due to the presence of different or variants of different diffusivities across compartments. DKI summarizes the deviation of non-Gaussian diffusion through the diffusion tensor. For example, in cases of well-aligned structures, this kurtosis tensor will show higher values in perpendicular directions to the fibers, where we expect to have more boundaries or more variances on diffusivities. Since DKI also quantifies the diffusion tensor, it also provides all the measurements that you can extract from DTI. For example, the mean diffusivity, the axial diffusivity, the radial diffusivity, and the fractional anisotropy. However, DKI also provides the kurtosis statistics. These are analogous to the ones that can be analogous to the ones that you extract from the diffusion tensor. For example, the mean kurtosis, the average of kurtosis of all directions, the axial kurtosis, that is the kurtosis along the well-aligned structures, and the radial kurtosis. One can observe that in opposite to the diffusivity values, kurtosis now will show the maximum values in well-aligned white matter on its radial directions. Moreover, you can also estimate the kurtosis FA, and as you can see from this figure, it provides a different information as the standard FA. To illustrate why quantifying kurtosis can be useful, let's consider the following toy model scenarios representing dense aligned structures, less dense aligned structures. For example, this can represent a healthy or a damaged white matter bundle. And also let's consider a case of structures that are crossing. For example, representing healthy intersecting white matter bundles. So if you look to the information of the diffusion tensor, we see that looking only to its anisotropy, it's hard to distinguish if a decrease on anisotropy is related to a decrease on the density of structures, for example, a damage, or just due to the presence of crossing fibers. The kurtosis tensor, however, can be used to distinguish these different types of scenarios. For example, if we look to the kurtosis tensors of these scenarios, we see that it provides lower magnitudes on the case of the damage toy model, while for the crossing fibers, its magnitude is still high. But in addition to that, it also presents distinguished slopes for the directions corresponding to the directions of the presence of the individual crossing bundles. This different information provided by the diffusion kurtosis tensor can also be seen by the DKI statistics maps. So for example, if we look to the standard FA, we will see that we have lower intensities on regions that we expect to have the fibers crossing. So for example, regions here, while the mean kurtosis extracted from the kurtosis tensors will show a more uniform values across all white matter structures. It is also important to note that while FA is very limited to target alterations in gray matter, because in the typical resolutions that we use, anisotropies are low, the kurtosis values on gray matter are non-zero. So this can be used to target difference, regional difference, or longitudinal on the gray matter. As I said, kurtosis also provides information of crossing structures. For example, this information can be used to resolve crossing fibers in tractography approaches. If you're interested on how to know how to do this, I recommend you to see this reference here. Another advantage of the DKI is since it captures the non-Gaussian information from multiple B values, this can also be used to extract information of average signals. So for example, if we average at each B value the directional information and we estimate the deviation of the linear decay on these average signals, we can obtain an index that is completely independent on the orientation or the presence of fanning or crossing fibers. So for example, I use this measurement on my PhD to target late maturations processes on aging that you could not observe on the FA maps due to the confounding factors of alterations on mesoscopic changes on fiber dispersion and crossing. Another advantage of this quantity is that it is more robust to noise artifacts. For example, a typical artifact that we observe in the standard DKI is negative values on white matter, and this is basically due to the difficulties of the model of capturing non-Gaussian information on well-aligned fibers, which radial directions have low diffusivities, and then though you don't have contrast to resolve non-Gaussian information. And this will provide artifactual low kurtosis that propagates to the mean quantities. By using this mean signal quantities, you improve the SNR, you avoid this lower diffusivities and individual directions, and you will get a metric that is much more robust. So you don't observe these negative values on this estimates. How can you fit DKI and DIPY? For this, the first thing that you need is data from multiple B values. So here we are downloading a multi-shell acquisition using the command line DIPY fetch. As for the DTI example presented by Ariel, we then mask the data to avoid calculations in the background. For this, you have to indicate the paths of the downloaded data or the path of your data if you have already multi-shell acquisitions. Then DKI can be fitted using the DIPY fit DKI function, where you need to input the paths of your data, the B values, the gradient directions of the data, and the mask. Just to indicate some limitations of DKI, as it is a phenomenological technique, it doesn't reveal direct biological properties. For example, DKI cannot be used to distinguish demyelination from axonal loss in healthy aging, so you really need caution on interpreting its results. As DTI, some standard DKI metrics can be biased by confounding, fanning, and crossing effects. However, in this talk I showed how you can use DKI or use a mean signal DKI to suppress this confounding effects. Another limitation of DKI is that it's based on the equation of a cumulative expansion. So it is inadequate to represent the non-Gaussian effects at high B values. So for DKI analysis, you should use moderate but larger B values than DKI. You can adjust the B values of your experiments according to the expected apparent diffusivities and kurtosis on your studies using this equation. So for example, if you assume that you have diffusivities around 1 microsquared milliseconds and kurtosis values are around 1, 0.75, you should use a maximum of kurtosis not larger than 3,000 seconds per millimeter squared. Okay, that is all for this talk. If you want to know more information about the implementations of DKI and DIPY, we recently submitted a preprint of a manuscript describing the implementations on bioarchive, and there you can see a more complete description of other DKI metrics that I didn't have time to present here, and also it gives some information how you can relate DKI with some microstructural models. So thank you for your attention, and bye.